Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from Jammu. Today we are going to discuss about a module entitled Atomic and Geometrical Structure Factors under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We will get the concept of atomic scattering factor. We will have a discussion on scattering of X-rays based on unit cells which are primitive. We will be discussing scattering of X-rays based on more complex unit cells, the concept of geometrical structure factor, derivation of expression and total scattering amplitude of X-rays in terms of structure factor of single cubic structure, namely BCC structure, body-centered cubic structure. Now, let us talk about structure factors, that's atomic scattering factor. We have considered scattering of X-rays on the basis of assumption that there are centers of scattering at the lattice points. However, one has to realize that the scattering is as a result of an interaction between the incident X-ray beam and the electrons of atoms composing the solid, no matter where the electrons are positioned. In other words, one must consider scattering of X-rays by continuous distribution of electron density associated with each lattice point. Let us consider an element of charge rho r vector dV located in an element of volume dV about the point r vector. Rho as a function of r vector represents the electron density, and rho r vector dV stands for the probability that an electron will be found somewhere in the element of volume dV. Let Z stand for the atomic number of the atoms composing the crystalline solid. The condition as given by the expression integral over V rho r dV is equal to Z as given by equation 14.1 obviously applies here. We shall proceed to determine the ratio of X-ray diffraction amplitude at the Bragg angle scattered by the element of charge rho r dV to the amplitude that is scattered by a single point electron located at the lattice point as is shown in figure 14.1. Here we compare scattered X-rays by the point electron at a point O and the radiation scattered at the Bragg angle by an electron density that lies within the element of volume dV. We shall find how different they are. Phi r is equal to twice pi by lambda dot r dot n given as equation 14.2. Let the amplitude of radiation scattered by the point electron at the origin O in the scattered direction N1 be represented by capital A e exponential of I into Ks minus omega t, which is given as equation number 14.3, where K is equal to 2 pi by lambda and S stands for distance coordinate in the direction ON1. The amplitude of radiation scattered by the electron density contained within the volume element dV at R will be proportional to the amount of charge in that volume element dV, and so will be given by rho r vector dV dot A exponential of I Ks minus omega t, which is expressed by equation 14.4, which will be out of phase by an amount phi r as given by equation 14.2. Accordingly, the scattering amplitude along n1 direction from the electron density within dV will be given by a exponential of I ks minus omega t plus I phi r dot rho r dV, which is expressed as equation number 14.5. Let the ratio amplitude of the radiation scattered by the volume element dV to amplitude of the radiation scattered by the point electron at the origin be equal to dF. Using equations 14.3 and 14.5, we have dF equal to A into exponential of I ks minus omega t plus I phi r dot of rho r vector dV upon A into exponential I ks minus omega t. Therefore, dF will be equal to exponential of I phi r dot rho r vector into dV. Using equation 14.2, dF is equal to exponential of I2 pi by lambda into r dot n dot rho r vector dV. Rearranging the terms, we get dF equal to rho r vector exponential of twice pi I by lambda into r vector dot n vector into dV, given as equation 14.6. Integrating equation 14.6 over all space, we have the ratio scattered amplitude of radiation from whole atom to scattered amplitude of radiation from a point electron at the lattice point equal to F equal to integration over volume V rho r vector exponential of twice pi I by lambda into r n vector into dV vector 14.7. According to equation 7.2 of section 7.4 in module 7, capital N is equal to twice sine theta. Therefore, twice pi by lambda into r vector dot n vector is equal to twice pi by lambda capital N r cos phi equal to 4 pi by lambda into r vector sine theta cos phi. Let us put 4 pi by lambda sine theta equal to mu, as is represented by equation 14.8. Now, let us assume that the charge density of the atom is spherically symmetric. It makes it to be a function of r vector only, consequently leading to rho r vector equal to rho r. We have from equations 14.7 and 14.8 the triple integral f equal to integral from 0 to infinity, integral within the limit 0 to pi, integral 0 to 2 pi, rho r, exponential of minus mu r cos phi dot r square sine phi dr d phi d phi is equation 14.9. The angular parts of this integral are solved first by integrating over phi, then over angle phi on putting cos angle phi equal to x, so that dx is equal to sine phi d phi, and then in the end expressing the exponential terms as trigonometric functions. This treatment gives f mu equal to integral from 0 to infinity 4 pi r square rho as a function of r sine mu r by mu r dr, referred to as equation 14.10. If scattering angle theta is very small, that is theta tends to 0, mu tends to 0, sine mu r by mu r tends to 1. Therefore, limit of f mu, mu tending to 0 is equal to integral within the limit 0 to infinity 4 pi r square rho r dr equal to integral from v to 0 rho dv equal to capital Z. Thus, if the scattering angle is very small, f is equal to integral within 0 to infinity 4 pi r square rho r dr, referred to as equation 14.11, which is the total charge of the atom including all Z electrons. Heavy, high Z elements produce a larger scattered intensity. In general, the scattered intensity will be less for large scattering angle theta than for small, according to equation 14.10. F is known as atomic scattering factor. The atomic scattering factors, which are also sometimes called the form factors, are given in the literature for the elements as function of sine theta by lambda. Refer international tables for the determination of crystal structures. Born-Traeger, Berlin 1935. The quantity just relates the amplitude of the radiation scattered by the electron distribution of the atom to that which would be scattered by an electron located at the center of the atom. Geometrical structure factor. The above discussion on scattering of X-rays is based on unit cells, which are primitive, having atoms only at the corners. What happens in case of crystals having unit cells which are more complex, such as base-centered cubic structures? For these structures, one must take into account interaction of radiation diffracted by different atoms in the unit cell. We consider H prime, K prime, L prime reflection. Let the ratio of amplitude of the radiation scattered by the entire unit cell to amplitude of the radiation scattered by a point electron at the origin be represented by capital F, H prime, K prime, L prime. F, H prime, K prime, L prime will be equal to summation over I, small fi, exponential of I phi I, which is expressed as equation 14.12, where Fi stands for atomic scattering factor for the ith atom in the unit cell and phi I for the phase difference between the radiation scattered at the origin and radiation scattered from the ith atom of the complex unit cell, and I equal to 1, 2, 3, etc., covering all atoms in the unit cell. From equation 7.3 of module 7, we know that phi I is equal to 2 pi by lambda dot product of Ri vector n vector, which is given as equation 14.13, where Ri vector is a vector from the origin to the ith atom of the unit cell. Taking A vector, B vector and C vector as the basis vectors, Ri vector may be written as Ri vector equal to xi A vector plus yi B vector plus zi C vector as equation number 14.14. But we know from equation 7.4 of module 7, 2 pi by lambda into A dot n vectors equal to twice pi h prime, which is equal to 2 pi n h. Similarly, 2 pi by lambda dot product of B vector and capital N vector is equal to twice pi k prime equal to 2 pi n k. Twice pi by lambda C vector dot n vector is equal to twice pi L prime equal to 2 pi n L, where H prime, K prime, L prime may be any three integers. In general, these integers may contain a largest integer, common factor, small n greater than unity, in which case we can put H prime equal to NH, K prime equal to NK, and L prime equal to NL, where H, K, L are three integers in the same ratio as H prime, K prime, and L prime, but having no common factor greater than unity. So, dot product of A vector capital N vector equal to H prime lambda. Similarly, dot product of B vector and capital N vector equal to K prime lambda. C vector dot N vector is equal to L prime lambda. Substituting for phi I from equation 14.13 in equation 14.12, the expression may be written as capital F of H dash K dash L dash equal to sigma over I F small fi exponential of twice pi I by lambda into dot product of Ri vector and capital N vector given as equation 14.15. Now, Ri dot Ni vector is equal to lambda into H prime xi plus K prime yi plus L prime zi, which is referred to as equation 14.16. Substituting for the dot product of Ri vector and Ni vector from equation 14.16 in equation 14.15, we have capital F H prime, K prime, L prime equal to summation over I small fi prime exponential of twice pi into H xi plus K yi plus L zi, put 14.17. Fi will have the same value F for all the atoms if they are identical, and so for a crystal with identical atoms, one can write the above expression in a simple form as capital F H prime K prime L prime equal to small fi summation over I to exponential of twice pi I H prime x I prime plus K prime yi plus L prime zi. Put summation over I exponential of twice pi into H prime xi plus K yi plus L prime zi equal to capital S, referred to as equation 14.18. Therefore, capital F H dash K dash L dash is equal to small f into capital S, which is given as equation 14.19. Expression at number 14.19, which stands for the total scattered amplitude, is thus given by the product of the atomic scattering factor small f and a factor capital S, which is defined by equation 14.19. Capital S depends on the geometrical arrangement of atoms within the unit cell and is called geometrical structure factor. Expression of 14.17 is a general form and applies for crystals where all atoms are not identical. The structure factor need not be real, and the intensity involves the absolute value of capital F, that is F star F. It is well known that the intensity of diffracted beam is proportional to the square of the amplitude. Expression at 14.19 suggests that the total scattered amplitude is equal to the product of atomic scattering factor and a factor capital S, which depends upon the geometrical arrangement of atoms within the unit cell. In the present case, the intensity of diffracted X-ray beam is proportional to the square of capital F, or more precisely to the square of the absolute value of capital F, or more precisely to the square of the absolute value of capital F being complex. Therefore, the square of the absolute value of F modulus square is equal to F star F, where F star represents the complex conjugate of capital F. Let the corner atom, whose location is at x1, y1, z1, be arbitrarily assigned the coordinates 0, 0, 0 to the unit cell, while other corner atoms are ignored and excluded from taking into account. The other atom in the unit cell of this structure is located at the body center and is assigned coordinates 1/2, 1/2, 1/2. Thus, for one atom, x1 is equal to y1 is equal to z1 is equal to 0, and for the other atom, x2 is equal to y2 is equal to z2 is equal to 1/2. Application of equations 14.18 and 14.19 leads to the amplitude of diffracted X-rays for H prime, K prime, L prime diffraction direction as therefore F H dash K dash L dash is equal to small f summation over I exponential of twice pi I H prime xi plus K prime yi plus L prime zi is equal to f into 1 plus exponential of pi I n exponential I pi into H prime plus K prime plus L prime as given by equation 14.22, where small f represents scattering power of an atom. The value of capital F is 0 whenever the exponential term, that is exponential of I pi into H prime plus K prime plus L prime, has the value -1. According to equation 14.22, the factor 1 plus exponential of I pi into H prime plus K prime plus L prime is 0 for any H prime, K prime, L prime diffraction for which H prime plus K prime plus L prime is an odd number whose exponential n pi I is equal to -1. If n is an odd number, the value of capital F is 0 whenever the exponential has the value -1. So, F is equal to 0 when H prime plus K prime plus L prime is equal to an odd integer. Capital F is equal to twice small f when H prime plus K prime plus L prime is an even integer. As such, capital F, H prime, K prime, L prime for a BCC structure contain H prime, K prime, L prime reflections which would be present for simple cubic structure having the same cell dimensions of its cube edges are missing. As for example, there are no reflections from 1, 0, 0, 3, 0, 0, 1, 1, 1 and 2 to 1 planes. However, there are reflections from 2, 0, 0, 1, 1, 0 and 2 to 2 planes. The same conclusion can be reached if one explains it by physically reasoning it out. That in the body-centered cubic structure, there are certain H prime, K prime, L prime reflections which are present in case of a simple cubic structure bearing the same cube edge dimensions get missing can be physically understood by referring to figure 14.2. As an example, for BCC structure, there is no 1, 0, 0 reflection, but 2, 0, 0 reflection does take place. Similarly, there is no 1, 1, 1 reflection, but 2, 2, 2 reflection is present. Let us take into consideration 1, 0, 0 reflection first. For simple cubic structure, the beams getting reflected from the top and bottom cube faces of the unit cell are out of phase by 2 pi for the 1, 0, 0 diffraction direction. This is not so in case of body-centered cubic structure. As an example, for BCC structure, there is no 1, 0, 0 reflection, but 2, 0, 0 reflection does take place. Similarly, there is no 1, 1, 1 reflection, but 2, 2, 2 reflection is present. Let us take into consideration 1, 0, 0 reflection first. That is, modulus of f square is equal to f star f. Now, capital F, H prime, K prime, L prime is given by equation 14.17. Putting capital F equal to alpha plus I beta plus and F star equal to alpha minus I beta. Therefore, modulus of F square is equal to F star F, which is equal to alpha minus I beta into alpha plus I beta, which is equal to alpha square plus beta square, where alpha is equal to summation over I within brackets small fi cos 2 pi h prime xi plus k prime yi plus l prime zi. Put this as equation 14.20. And beta is given by summation over I within brackets small fi sin 2 pi into h prime xi plus k prime yi plus l prime zi. Put this as equation 14.21. Some examples. Structure factor of simple cubic structure. A simple cubic crystal has only one atom per unit cell. So the diffraction amplitude for HKL diffraction is S is equal to F. It means that all lines that are predicted according to Bragg law will appear provided the atomic scattering factor small f is large enough to render the intensity peaks observable. Now we will come to structure factor for BCC lattice. The basis of BCC structure of a cubic unit cell has identical atoms at 0, 0, 0 corner atom and 1/2, 1/2, 1/2 for atom at the center of the cell. For one atom, x1 is equal to y1 is equal to z1 is equal to 0, and for the other atom, x2 equal to y2 equal to z2 is equal to 1/2. Therefore, capital F, H prime, K prime, L prime is equal to summation over I, small fi exponential of twice pi I, H prime xi plus K prime yi plus L prime zi will become capital F, H prime, K prime, L prime equal to small f within the brackets 1 plus exponential I pi into H prime plus K prime plus L prime, where small f represents scattering power of an atom. The value of capital F is 0 whenever the exponential has the value -1. The geometrical structure factor capital S is equal to 1 plus exponential of I pi H prime plus K prime plus L prime is equal to 0 when H prime plus K prime plus L prime is an odd integer. S equal to 2 small f when H prime plus K prime plus L prime happen to be even integer. These intermediate planes also diffract the X-ray beam. Since the density of atoms constituting the intermediate planes is the same as that of top and bottom cube face planes, they result into diffracted beams of intensity, which is the same as those due to top and bottom planes of the unit cell. As one can visualize from figure 14.2, the diffracted beams of X-rays due to top and bottom cube face planes, though have the same intensity as those diffracted by the intermediate planes but are out of phase by pi radians, it leads to a situation in which the diffracted beams from the top planes and body center planes interfere destructively in pairs, with the result that there is no net diffracted beam under these set of conditions. Now, In the BCC structure, there is no 100 reflection. Now let us consider 200 reflection. In that case, the top and bottom planes produce beams which are out of phase by 4 pi. The intermediate planes due to atoms at the body centers give rise to beams which differ in phase by 2 pi from the reflection by top and bottom planes, leading to their reinforcement because of constructive interference rather than their cancellation. Destructive interference. Similar arguments can lead to explanation of other missing reflections for the BCC structure. 14.2 shows 100 and 200 diffraction angles in a BCC structure showing phase relations leading to cancellation of beam pairs and reinforcement of beams. As an example, for BCC structure, there is no 100 reflection, but 200 reflection does take place. Similarly, there is no 111 reflection, but 222 reflection is present. Let us take into consideration 100 reflection first. For a simple cubic structure, the beams getting reflected from the top and bottom cube faces of the unit cell are out of phase by 2 pi for the 100 diffraction direction. This is not so in case of body-centered cubic structure. In this structure, having the same cube edge dimension, there is an additional plane of atoms which is due to atoms positioned at body centers. This additional plane formed by atoms at the body centers of the cubic cell is parallel to and located halfway between the top and bottom cube face planes of the unit cells. So, students, let us summarize what we have learned in this module. We had the concept of atomic scattering factor. We discussed scattering of X-rays based on primitive unit cells. The quantity related to scattering of X-rays based on more complex unit cells like bay-centered cubic structures is discussed. Concept of geometrical structure factor is explained. Expressions giving the total scattered amplitude of X-rays has been derived. Structure factor of simple cubic structure and BCC lattice is described. Thank you.